Thanks, Kevin, and thank you all for being here. It's tremendous to see so many excited faces in the audience. So this talk sort of pairs with Matei's talk you might have seen in the morning, in that it provides a little bit more of a speculative vision for what the PIs on the Dawn project sort of view as the potential for usable machine learning at scale. And specifically, we're going to ask the question, what is the potential for machine learning and AI tools? And specifically, what are the trends that we're seeing in terms of AI and ML technology, and how will they impact both science and enterprise as machine learning becomes more accessible, more usable, and more widely deployed at scale? So just to sort of recap, I think this is really almost reaching critical excitement behind ML and AI. And from one perspective, ML and AI are really picking up where big data left off, right? We sort of convinced the C-level executives in the room that data is no longer expensive to store and manage, right? It's no longer a cost on the balance sheet. In fact, data today is valuable and relatively inexpensive to store, okay? And ML, by and large, has come in and said, okay, now that we have this data that's valuable, let's do something with it, right? Simultaneously, a number of other shifts have occurred over the past several years, where yesterday, compute was expensive and hard to scale. It's fairly expensive to provision more servers in a data center computing environment. And today, compute is cheap. It's elastic. We can get a wide variety of computational substrates on a variety of cloud providers. Distributions basically everywhere. And perhaps most excitingly, certainly in terms of the headlines that we see, we've moved from a model where maybe we could get some sort of better than human accuracy on classically challenging tasks. Whereas today it seems like almost every month there's a paper, many of them published by my colleagues at Stanford, showing that we can sort of outperform humans on many particularly challenging tasks, whether or not it's lung cancer diagnosis or skin cancer diagnosis or just classic image detection. So, or image classification. So these are all really sort of exciting, and I don't think I have to convince anyone that sort of AI and ML are certainly promising. But the challenge that we see today is that it's very hard to actually build out models. And Matei did a great job covering these points in the morning, so I don't want to belabor the point, but there are a wide variety of challenges pertaining to building and deploying models that are not addressed today by commodity infrastructure. So, answering questions like, what data do I have available in my organization? Right? What data sets could I use in order to build a predictive model? And even if I have the data, how do I label this data? And should I trust each of my data sources equally? Once I have my data and my labels for my data, how do I specify a model? And which of the many architectures should I train? Depending on which year of the machine learning conferences proceedings that you read, you'll get a different answer. More importantly, if my results are poor quality, as they often are when we initially apply machine learning to a particular data set, how do I understand what's going wrong? Is it my model? Is it my training data? Is it something about my training process? And how do I trust my model is good enough in order to deploy in practice? Provided I have a predictive model, which is usually where the story stops for a lot of machine learning papers, how do I actually integrate it in my application? What does a predictive word processor look like? What does a predictive CRM look like? Right? If we're doing things other than just image classification on benchmark data sets, integrating these things into applications is non-trivial. Not only because the programming interfaces don't exist, but also because the computational requirements for inference are particularly expensive. And in an ideal scenario, we would continuously learn from our deployed models. So all of this is to say is that there's a lot of missing pieces which practitioners essentially hand roll from scratch today that we think can do much better. And Matei showed this slide in the morning. Right? Hidden technical debt in machine learning systems from our friends at Google. This paper claims that only a fraction of real-world ML systems is composed of ML code. It's the black box right here. And naturally, the missing pieces are essentially answering all of the questions that I posed before. So if I want to perform data collection or labeling, today it's essentially an ad hoc process. This is why in the Dawn project, we're building this new stack for usable machine learning, addressing a number of these different machine learning lifecycle phases from data acquisition to productionization. But in this talk, I want to step back and ask, what does it really mean to build out a stack for usable machine learning? What will this usable machine learning actually enable? And specifically, why does machine learning usability actually matter? Well, the short answer is that the faster we can put models into production, the better data we can obtain. And subsequently, we can obtain better models. So in contrast with a typical software development life cycle, which is essentially happening at very, very coarse-grained timescales, we can continually improve our models. And in this talk, I want to dive into the details of exactly what this means from a technical perspective and what this technical perspective will mean for enterprise use cases. So we wrote a paper a while back. This was actually back in 2015 when I was still in the AMP lab where Matei and I were graduate students. And one of the ways that we found it helpful to visualize this was sort of as a continuous cycle between data that is trained to produce models, models that are served to produce actions, and then the sort of critical part here is this final linking step from action back to data where we observe the effects of our models. And this is a fundamentally different way of building and deploying applications. Now, fortunately, unfortunately for this Velox project, this paper here, it sort of remained paperware. There was a few sort of follow-on projects, but the good thing is now that I'm a professor at Stanford, we actually get to go out and build this thing for real in collaboration with our partners. So why is this training data so critical, right? Ultimately, this cycle is enabled by data, and it's all about data flowing through this loop. Well, to illustrate this point, I'm going to draw on one of the most sort of thought-provoking studies we've seen in the lab over the past several months, which is a paper from Google revisiting a claim made by actually Peter Norvig and some colleagues a while back about the unreasonable effectiveness of data. So specifically, Norvig and colleagues noted that especially at say, Google scales, more data essentially tended to beat better algorithms. Okay? This was a great sales pitch for working at Google, but it also tended to be relatively true. We can capture the long tail of data, use relatively simple models, and the more data, the better results. And this paper, which appeared in the archive in August, essentially looked at this problem in the context of deep learning, which is enabling many of the advances we're so excited about in machine learning. In this paper, there's a really sort of exciting study. The core sort of takeaway from this paper is that if we scale up the number of examples or training data dramatically from 10 million, which is sort of what's available in public data sets, all the way up to 300 million labeled training data points. This is using some weak supervision, but they're essentially fairly high quality training data points. The deep learning models here continue to improve. You see the accuracy continues to go up and to the right. And essentially for a linear increase in training data, we get a logarithmic increase in accuracy. So this is pretty exciting. It means that if we have millions of training data points, we do even better on our models. But as we're interested in sort of usable ML at Stanford, we ask the opposite question. What if we have less training data? We essentially, following this study, repeated the same study, but we took the reference standard ImageNet model and scaled it down. Okay? So this plot here essentially replicates the study in the case of image classification on the ImageNet training data using a state-of-the-art image classification model. And what we see here is a similar trend. As we increase the number of images per class from 100 to 1,000, we see a logarithmic increase in validation accuracy. And for top 5 accuracy, we get up to something like 92% without really tuning the parameters of this model. The more exciting thing about this, from my perspective, and I'm going to really hammer this point home in this talk, is that if we don't look at this sort of log linear plot, but we plot this as linear, so this is the same plot just with different axes, we actually see a pretty interesting trend. Specifically, we see this sort of logarithmic curve become incredibly apparent. And this logarithmic curve is going to have profound implications for how we actually deploy usable machine learning. Now, so this logarithmic curve is essentially inverse exponential. And as we all know, looking to history, exponential curves have a tendency to define technical fields. Right? Does anyone know what this curve represents? I've obscured the y-axis, but the x-axis is time. Moore's law, right? So this is Moore's law. If you think about what Moore's law meant for computing, it essentially said that we could sit back and essentially wait for processors to get faster and faster. We didn't have to worry about parallelism until, of course, this stopped in recent years. So when we see sort of exponential curves like this, sort of my Dave Patterson and John Hennessy mind sort of starts to go wild because it's very, very hard to beat an exponential curve. When we look at this sort of logarithmic curve between training data and validation accuracy, we should start thinking about what this is going to mean for usable ML. Specifically, I think there are sort of 3 really exciting regimes that this curve represents. The first of which is that at the very low end, with very small amounts of training data, it's easy to obtain sort of modest quality of models. With only 100 examples per class in ImageNet, we can get about 70% accuracy. Certainly not going to fool any human, but it's actually reasonable enough if we want to, for instance, reduce some of the workload that we're placing on, say, humans when they're performing, say, image classification routines. More exciting, as we move up the curve, we start to get relatively large gains quickly. In fact, it's pretty fast to move up this curve with a small amount of training data. This is sort of the blessing of this logarithmic curve. But of course, at the high end, right, once we move up to sort of best-in-class accuracy, this curve starts to hurt us again. Because it essentially says that for linear increases in training data quality, or sorry, for linear increases in model quality, we need essentially exponentially more data. So I want to unpack each of these three regimes. I think they're critical to understanding why usable ML is so exciting. Just to pause here, in case you're not familiar with these sort of, this idea of training data or these images per class here, these machine learning models take in a large number of labeled examples that are best when they're sort of domain specific. That is, they're particular to, say, medicine or finance or whatever application we're trying to perform predictive models. They're human readable, or sorry, machine readable, right? So just you and I can read a sentence. We need to put, say, text sentences into a way that machines can understand. And they're best when they're highly precise and unambiguous, right? Computers aren't good with ambiguity. Of course, there's a bunch of research projects and ongoing work trying to use less precision and more ambiguity, but basically there are few substitutes for the real thing. And this really, really matters when we think about the fact that detecting cats and dogs as an ImageNet is pretty easy, but getting a lot of labeled training data that's highly precise for things like radiology, some of the stuff we do with folks in the med school today, that's a lot more expensive. So let's unpack this curve a little bit. I think this is probably the most important part of the talk. I'm really, really excited about what this means for usable machine learning. Let's start at the high end. So I said it's extremely expensive to improve model quality when we're at very, very large degrees of accuracy. And what this means is that organizations which can obtain large amounts of training data will obtain defensible advantages in scenarios where accuracy is key. So if we're in medicine or autonomous driving or finance or, say, precision manufacturing, training data, getting up to that sort of best-in-class accuracy will essentially become a competitive advantage, right? Especially in a vertical-specific context. If I can collect the equivalent of ImageNet for medicine, or for my particular branch of medicine, more likely, right? So say lung cancer radiology, that will become a critical asset that I can use as a defensible sort of advantage in my business. Now, the opportunity here is that this is really, training data is really a moat, right? It's incredibly exciting. But it's also a caveat, and that's very hard for any one organization to span all verticals, right? So on the one hand, it's unlikely that the big, quote, fearsome four will actually sort of have the best training data in every single vertical in the world. However, it's very, very hard so it's unlikely that the fearsome four will just sort of dominate every vertical. On the other hand, it's unlikely that so it means that basically, almost anyone can come in today, or likely can come in today, and start to build their own high-quality training data sets. So if this is the high end, where essentially training data is a defensible advantage, let's look at the low end. So at the low end, given that it's easy to obtain modest model quality, tools that make it dramatically easier to get started on this curve can really amplify the potential of machine learning. So we can likely put models into production relatively quickly, albeit with relatively poor quality. So we're probably not going to replace a human with a small number of examples, but it's perhaps easier than we thought, provided that we can actually express models and put them into production to actually start to make inferences. Moreover, once we actually put these models into production, we can start to rapidly move up the curve, right? So by putting models in production and obtaining feedback, we can quickly ramp up model quality into sort of a defensible asset. And so the really exciting thing here in our bet is that organizations that are just getting on this curve today can dominate their verticals tomorrow, right? Especially given that no one organization is likely to have training data for every single vertical application. And so we think this is really exciting in terms of a greenfield potential for machine learning adoption, right? The name of the game is basically putting models into production quickly or obtaining large amounts of training data in order to obtain this type of defensible advantage. That's what this log linear curve teaches us. So the bet that we're placing is that tomorrow's vertical leaders will be enabled by the production, collection, and use of training data, which is why building these tools is so critical to the vision of usable machine learning. Now, 2 points I just want to make very quickly is as we integrate these machine learning functionality and capabilities into applications, it's going to change the way in which we program. So in the old world, sort of in what we do today, by and large, that software improves when we improve it, right? So if we want to update a software library, we do so manually, by say changing the manifests in our source files to basically pull in the latest libraries from the internet, or alternatively push changes manually from our from sort of coding with our engineers. In the new paradigm, sort of software that's enabled with machine learning will actually continuously improve, right? And we'll have to have new primitives. This is a pretty dramatic shift in terms of the way that we actually write applications today that continuously observe the effect of the actions it's taking and then react to it to sort of complete that funnel between not just the data we have, but the actions that we're performing on behalf of the data. So closing that loop will require sort of new programming interfaces, of which we're building some of these in Dawn and of which we expect others to build over time as well. And this really means that ML will shrink release cycles. So machine learning today and data science today is an inherently iterative process. By and large, the faster we can release, the better models we'll obtain. What this means is that we're going to shift in some verticals like automotives from a yearly or multi-year release cycle to one in which we're shipping new models overnight. And among other things, this means that monitoring machine learning will become a critical bottleneck. Now, in the interest of time, I'll only briefly mention that we think this is going to be, that realizing this vision will require a combination of better interfaces, reusable components, and tools and services to build out the remainder of that stack and make it so that we can get people onto this curve quickly. And before I conclude, I'll just leave with one final thought, which is inspired by one of Matei and my sort of technical mentors back at Berkeley. This is Ali Ghodsi, who's now CEO of Databricks. And in a sense, Ali has this amazing observation that in some sense, we've only started to solve the easiest machine learning problems. So from a statistical point of view, problems with lots of labeled data, like the problems we see being applied in, say, web search and web scale data, are relatively simple to solve. You don't even, with enough labeled training data points, we don't even need deep networks, right? We can simply run, say, nearest neighbor classifiers. When we have a new point we want to classify, we say, which among the billions of examples I have is most similar to this one? I'll say, well, dog is similar to this one. I'm going to label this thing a dog. So the challenge is going to be basically, in the future, making it so that when we don't have lots of labeled data, we can start to make productive use of the data that we have. In the future, we believe the key to useful machine learning will not be better architectures or cost models, as we see in a lot of the machine learning work going on today. We'll likely have good standard models and/or model search procedures that can search the space of model architectures and kind of get us reasonable quality results. The key to future success in useful machine learning will be all about data quality and large amounts of high quality data. So our bet is that by delivering tools, enabling organizations to get on that accuracy data curve and ride it upwards by deploying applications, getting feedback on how predictions are being made, and starting to build up that trove of defensible training data will be incredibly disruptive across science and industry, right? We've seen this in very narrow domains. We believe by building tools that democratize access to these types of predictive capabilities and close this loop between data, models, and actions will be incredibly disruptive. And this requires a redesign of the modern software tool chain. There's just a huge amount of infrastructure to build out in order to make this possible. It's almost as if we're at the beginning of the web era and we don't have relational databases and web servers. So I'd love to take questions and would love to chat with you afterwards. Thank you so much.
We have time for, I think, 2 or 3 questions. If someone would like to use the microphone.
So in your slide of questions, you kind of showed a variety of things, including one which was how do you integrate it into applications? And even here you slightly hint at observing actions, but what you don't get at is it sort of comes from a perspective of upselling machine learning rather than saying there is an application. Where are the places to make the biggest bets? How do you understand the data you have to actually target the right thing? So starting from applications and logs, how do you triage and determine where your investment should be, rather than how do you sort of hammer in machine learning into there, but sort of do a top-down approach to it. Do you have any thoughts on that kind of approach?
Yeah, so let me make sure I understand the question. So essentially, we talked a lot about, given an existing application, how do I fit ML inside of here? But there's this question, where in my application can I even benefit from, say, predictive tasks today? Is that right? Yeah, I think it's a really interesting question. It's one that we'll certainly see sort of start to evolve more and more over time. I think if you look at a lot of, if you look really broadly at, say, tech startups today, many tech startups, the Ubers, the Airbnbs of the world, even Facebook, they're not necessarily enabled by, they're not necessarily tech. Like Uber is really a transportation company enabled by tech. And I think that the biggest, advancements that we'll see are from taking sort of these classically entrenched verticals and actually saying we can do much better, we can reduce costs or improve efficiency or enable sort of functionality like on-demand, say, rides in the case of Uber and Lyft in ways that we couldn't have thought of doing before. So it's difficult to predict exactly where the biggest bang for the buck will be, but I do think that by providing toolkits that people who don't want to come and get a PhD at Stanford in machine learning and don't want to understand all of the data engineering challenges and build it all from scratch so that they can get started will enable the next class of applications that we probably haven't thought of yet. And I think that some of the work we're doing now on asking what are these interfaces, what is the equivalent of like the SQL or the LAMP stack for, say, web applications that enabled Web 2.0 to take off. These will enable these sort of non-expert users, but relatively capable programmers to start building up those other sorts of technologies. Yeah.
I see our next speaker is here. We have time for one more question. If, Phil, you want to plug in while we take one, if there is any more in the audience. Please, to the mic. Can you unplug and
Sure.
we'll get set for the next.
My question is about the results that come out of these tools. And by way of a quick example, years ago, this is about 8 years ago, and it wasn't truly machine learning by today's definition, but so we had a tool that was looking for potential cases of fraud. And it would find these interesting transactions, but it was really bad at explaining, so that this would end up in front of an analyst, and it was really bad at explaining how did this transaction end up in front of an analyst. So a lot of these tools are increasingly more and more black boxed. And especially if you work in a financial space, typically if you're applying this to credit models, something, you have to explain to people how you ended up with the results you did. So I'm curious your thoughts on not just how do you build these models to become better and better, but then how do you have these complex models explain back to a human how it ended up with its results?
Yeah, no, it's a great question. I think this idea of model interpretability is incredibly critical to deploying, especially in cases where we have regulatory concerns around fairness, and so on. This is a topic of a lot of research. I think the verdict is still out in terms of the best way to produce interpretable model results. But certainly, colleagues from Chris Ray to John Ducci, even some of the work we've been doing on this macro-based engine, address various parts of this. I think most optimistically here, I do believe that if you look at the new types of interfaces we're providing to users to, for instance, express rules or heuristics about their training data, such as Chris Ray's Snorkel project, where we can even use natural language explanations of what's going on in data to generate training data. So this is all about getting more labels. There's a possibility, I think a very strong possibility, that we can use the same high-level interfaces for domain experts to explain model predictions. So if I can go from natural language text to a labeling function in Snorkel, as some of Chris's and Percy's work shows, then it should be relatively simple to invert that process, such that when I have an explanation, I can at least go back to my set of heuristics that I've expressed about a training data point and actually produce natural language explanations. So that's certainly the dream. We haven't done it yet, but I think that these higher level interfaces have implications for not just allowing domain experts to specify what they know, but also for the model to report back what it knows and what it thinks that the domain expert has tried to tell it. Yeah. So, great question. Thanks.
Thanks, Peter, once again.